Hey everyone, welcome back to another exciting episode on chemistry. We're coming close to the end of the school year and I'm hoping everyone is staying safe during this time. Okay, so for today's lesson, we are going to be looking at a pH scale. What is a pH scale? And lastly, how do we calculate the pH of solution? Okay, so first of all, what does pH stand for? pH stands for power of hydrogen. So what does that mean? Every time you have a solution, depending on that solution or that substance, there's going to be a certain concentration of that hydrogen ion, and depending on how much you have of it, that would determine the pH for that solution. Okay, a pH scale, it's on a number scale from 0 to 14. So if the solution, if the pH is greater than 7, it's going to be considered basic. If it's less than 7, it's acidic. And if it's equal to 7, it's going to be considered neutral. Okay. How do we measure the pH of a solution? There are several things we can use. We can use, a pH strip, like litmus paper, for example. We can use an indicator, like universal indicator, or we can use a pH meter to measure the pH of a solution. Okay. Let me show you an example. Here are some common substances on a scale of 0 to 14, the pH scale. So, for example, lemon juice, typically it's around 2 for the pH. Toothpaste around 9. Household ammonia, the pH is around 11 because it's basic. And pure water typically is going to be 7 for the pH. Okay. All right. So let's start going over how to calculate the pH of a solution. Okay. So for example, let's see you have this. Let's say I have a solution. Example. Okay, let's say this. Okay, let's say I have a solution. Let me draw this. Okay, all right. Okay, so there's a solution. Let's say it's a HCl. Hopefully, y'all know this is considered an acid. What's the name of this acid? This is called hydrochloric acid. Okay, and for this solution, the pH is equal to 3.52, and it's at 25 degrees Celsius. Okay, why don't we start by just kind of reviewing how to write an equation for this, okay? So, first of all, HCl, it is considered a strong acid. So, for a strong acid, it's going to completely dissociate into the ions, okay? So, how do we write an equation for this? So, we'll say, hey, HCl. So, imagine, as you put it in water, put aqueous, it's going to completely dissociate. So, I'm going to put a single arrow. Forward reaction, giving you H plus, aqueous, and your Cl, which is your chloride ion. Okay. So what we can do is using the pH, we can calculate how much of that hydrogen ions are present in that solution. Okay. And of course, there's an equation we can use to help us figure this out. Okay. So your H plus ion, concentration of your H plus ion, okay, is equal to 10 to the negative pH. So based on this equation here, I'm simply going to plug in my pH. I'll show my work. So H plus equal to 10 to the negative 3.52. So with your calculator, you have to put in the numbers 10 to the negative 3.52. And you're going to get this very, very small number. It's going to be 3 point, I'm going to put a scientific notation, 10 to the negative 4. Since I'm asking for the concentration, I typically use what? molar for molarity. Okay, for significant figures, slightly different when we're looking at a pH. Okay, so rule of thumb is this: make sure you look at how many numbers to the right of the decimal. Since it's 0.52, there has to be two significant figures for the concentration. So hence, it's 3.0. That's two significant figures. Okay, let's take a look at one more example. All right, let's say, here's the last example. I have a pH. Solution with a pH of 12.15. Okay, and again, this is, we're going to assume it's all at 25 degrees Celsius. If I don't say 25 degrees Celsius, you're just going to assume it's 25 degrees Celsius, which is room temperature. Okay, so 12.5, 1.5. So this is, again, since it's greater than 7, it's going to be considered a basic solution. Okay. Oh, and by the way, depending on if it's acidic, basic, or neutral, it'll tell you, how much of the hydronium ions do you have in that solution, or how much hydroxide. Okay, so typically, if it's acidic, you're going to have more of the hydronium or your hydrogen ions compared to your hydroxide OH. Okay, if it's basic, more hydroxide, OH negative, and of course, if it's neutral, the same amount of H plus and OH minus ion. Okay. So let's say this. Let's say a solution with a pH of 12.15 at 25 degrees Celsius. And let's say the solution here is, let's say it's sodium hydroxide. Okay. Again, sodium hydroxide, typically that's a strong base. So let's say you were to, write the equation for this, you're going to say, it's going to be aqueous. As you put this in water, it's going to completely dissociate into its ions. Okay, to its ions. So what you can do is, we can figure out how much of the hydroxide ions are present in there, and there's also going to be some high hydrogen ion present in that solution as well. Okay, so notice this time it's the pH is 12.15. Okay, so what I can do is, hey, I can do H plus. Okay, set it equal to 10 to the negative pH. Plug in my pH, 10 to the negative 12.15. Okay, let's go down. Okay, so I'm going to take my calculator. Now you're going to get, again, let's go ahead and just do the sig figs too. So you have 7.0, excuse me, oops, 7, I'm going to round it. So it should be 7.1 times 10 to the negative 13 molar. Okay, this solution we know contains, 7.1 times 10 to the negative 13 molar of your hydrogen ion. So how do we calculate how much of the hydroxide ions do we have in this solution here? Okay, so if you remember from last time, I talked about the ion product constant, which says you're at 25 degrees Celsius, your Kw is equal to your, H plus times your hydroxide. Okay, what is Kw from last time? This is something that based on experimental value, it's 1.0 times 10 to the negative 14. Set it equal to 7.1 times 10 to the negative 13. And I'm going to solve for the concentration of OH here, because we're trying to figure out how much of the OH do you have in this solution here. Okay, so there you go. We're going to use the Kw constant. And now I'm just going to solve for it by dividing it by taking 1.0 times 10 to the negative 14 and dividing it by 7.1 times 10 to the negative 13. And you're going to get 0.014, and it's going to be two significant figures. Okay. Oh, there you go. The OH concentration for this is 0.014 molar. Okay. And again, in this solution, you're going to have some hydronium or your hydrogen ions present as well, which is going to be 7.1 times 10 to the negative 13. Since it is base, you're going to have more hydroxide or more OH concentration. Notice the 0.0114, it's greater than 7.1 times 10 to the negative 13. Okay, so just to recap, for your equations, okay, if you're given the pH and you want to find the your hydrogen ion concentration, it's 10 to the negative pH. Okay, the opposite of that, let's say you want to find the pH of solution and you're given, I don't know, the hydrogen ion concentration. Well, it's pH equal to the negative log of the concentration of times the concentration of H plus. Okay, and again, assuming it's at 25 degrees Celsius, room temperature, we can use the Kw constant sometimes to solve for either the H plus concentration or your OH concentration in a solution. Okay, and again, Kw, what's the experimental value? It's going to be 1.0 times 10 to the negative 14. Okay, it's never going to change unless it's not at 25 degrees Celsius.